So again, good morning, everyone. We're going to go on to semiconductors. So if you didn't know, with AC theory last week, we did start module 2. All right, so we're continuing on into module 2 with semiconductors. We will discuss after class whether or not we are taking this into next week. All right, or we're going to wrap up with this one. So we'll see how you all feel. Now, this handout is a lot of reading. Right, you're going to see there's a very big overlap between chemistry and physics in this point, because at chemistry you all look at bonding and energy levels and whatnot, which is what we're going to look at here today. So reading from our handouts, a lot of reading. Right, I think there's no maths in this handout. We reach a physics handout without any maths. That's really sad.
The day has arrived. Yes.
Right? Yeah, there actually is no mathematics in this topic, but there are a lot of things to remember. Don't worry, that's only for this little piece. So semiconductors. You all have heard about semiconductors before. We all knew it was this special material that allowed electricity to flow in one direction. What does that mean? How can electricity just flow in one direction of a material? Are there channels? Is there somebody, a one-way drive or road and somebody stopping the traffic? How on earth can we have a material that is going to allow electricity to flow in only one direction? So it's a really special um, quality or characteristics of these materials. We only have a few semiconductor materials, and that's to tell you all, without a semiconductor diode, the world of electronics, digital electronics, will not exist. And quite frankly, everything in the world right now needs digital electronics, i.e., computing and radio signals and internet signals. Everything we do today in this world, basically our life revolves around these types of materials. So let's read. A semiconductor is a material that has a conductivity level somewhere between the extremes of an insulator and a conductor. Semiconductors have negative temperature coefficient. We're going to introduce some new terms here that I do suggest you all read up and know what they say, because this is going to come in an equation later on, not in this one though. All right, so semiconductors have negative temperature coefficients of resistance, meaning that their resistivities decrease with increasing temperature. In regular world, in regular materials, when the temperature increases, we know that our resistance also increases. Why? Because our materials start moving, our atoms and our free electrons start moving around a lot more haphazardly and not allowing for the free flow of electricity. So the beautiful thing about a semiconductor, it works better when it gets hot, which is why your computers actually can work at pretty high temperatures, right? You all ever realize that your phone, your laptop, your computer gets pretty warm? That's why we need a whole bunch of fans in our systems, right?
Yes, yes, yes,
Right?
yes.
Why? Because inherently these materials work better in heat. And with all of these small electronics, they are going to generate a lot of heat. Why a lot of heat? Because if we remember, this is where we bring in all our physics. The thinner our wire, right? The thinner our wire, the greater the resistance and the greater the heat. And remember, we did this in transformers. When we wanted to get rid of heating in our transformer, instead of using thin wires, we use thick wires to minimize that heating effect. In a computer or any other microelectronics, there's no way we can use a thick wire. So the inherent nature of our circuitry will generate a lot of heat. So wonderful that the one thing that maintains our electronics and working, yeah, I say heat, bring it on. We'll work better in heat. All right, so continue reading. The extent to which a semiconductor conducts electricity is affected considerably by the presence of impurities. Now, we are going to live right now in opposite world, right? We know that the presence of impurities do nothing good. They decrease your conductivity, or they increase your resistivity. They're going to make it more brittle. Sometimes they are going to change the nature of the material where it's not that predictable. But for a semiconductor, one, it works better under heat, and two, it works better when there are certain impurities in it. We're in opposite land right now. So continue reading. Very pure semiconductors are called intrinsic semiconductors. So, no, I have seen this come in exams quite often for you all to be able to distinguish between your types of semiconductors. So, very pure semiconductors are called intrinsic semiconductors. Those to which impurities have been added are called extrinsic semiconductors. So we have to be able to distinguish between these two types of semiconductors. So let's look at intrinsic semiconductors to start with. Silicon and germanium are tetravalent, and both elements are crystalline, crystallized, or crystalline with diamond-like structures. Chemistry people, what does tetravalent mean?
It's for covalent.
We have four covalent bonds. Woo, who has a mic on? Okay. All right. Tetravalent means that we have, if we look at it, we have four bonds available to do our bonding, which is one of the best kind of bonds to make because we know that the outermost shell, especially in this level of atoms, has 8 covalent bonds that it can make. So the fact that it has 4 covalent bonds means that it can bond to 4 other atoms very strongly and in a diamond-like structure, just like carbon in its diamond-like structure. Right? We know that carbon undergoes a tetravalent. Does carbon undergo tetravalent? Yes, it does. All right? To give us, when it undergoes this kind of bonding, that's how we end up getting our diamond-like structure. Same thing here with for silicon. Pure silicon is a crystal. Anybody knows what's the most common silicon compound on the planet? Starts with S.
Starts with what? S?
Starts with S. What is the most common compound of silicon on this planet? And we are all missing it a real large amount right now. Having our feet in it, and in our hair, and in our swimsuits.
Look,
Rubber.
What?
Sam.
Sand.
Oh, oh.
Sand is silicon dioxide, and silicon dioxide is one of the most common materials we have on this planet because at every beach we have silicon dioxide in some form or fashion. And trust me, we are all missing some silicon dioxide in our life right now. Well, we're missing the water more, but we need silicon dioxide too. Because when you all go to a beach with rocks, it's not fun. All right. So silicon and germanium, they are in the same column in the periodic table, just different rows. All right, so they are tetravalent. They are both crystalline and they have diamond-like structures. At 0 Kelvin, all the valence electrons are involved in bonding. So this is where we are going to look at how temperature affects our bonding. So at 0 K, not OK, we've had that joke already. All right, so at 0 Kelvin, all valence electrons are involved in bonding. So the crystal behaves like a perfect insulator, meaning there are no free electrons available to allow for the conduction of an electric current. So at 0 Kelvin, our semiconductor is an insulator. There is not a single free electron available to allow for the transfer of electricity in the material. But as temperature rises, free electrons begin to move about. When an electron escapes from the bond, it leaves behind a vacancy in the lattice, and this vacancy is called a hole. Now, we are going to name anions and cations different names in semiconductors. So, when I have an atom and a hole has been created by the removal or by the escape of an electron, what do I now have? What kind of ion do I have? Let's see that better. When I have an atom that has an electron that has escaped, that vacancy is called a hole. But what is that ion that has been created now, that has now been created? What is it going to be called? We're talking about ions, y'all. There are only two types of ions.
Cation.
A cation. All right, so here your cations, right? Your cations are called holes, which makes sense. There's a space, there's a gap in your lattice, there's a gap in the whole bonding of your materials that has now been created because that electron left. So we called
Oh wait,
cations. What?
cation are positive and the electron negative. So it wouldn't
Yeah,
take the so it wouldn't be the negative ion that
sweetie.
taking.
When the atom loses an electron, what is going to happen to its overall charge?
I honestly had no idea, you know.
Moving on. While I think Jabari had too much sorrel already for this season. It's only December 2nd, dude. All right, so hello, look at here. If you read, all right, so it's essentially a positive charge. This hole will readily accept a free electron. The apparent movement of free electrons and holes results in an electric current being formed. In semiconductors, there are two types of charge carriers. Now, there's one actual charge carrier and one that happens as a result of the movement of something. But we still call it in the topic two charge carriers. So, what we have are our two charge carriers. We have free electrons and which are negative, and holes which are positive. Free electrons are those electrons that have been liberated or they gained enough energy to leave the silicon or the germanium lattice, and they are now free to move about. And because we lost that electron, the lattice that it was in, lattice being the structure that it was in, is now missing an electron, so it's going to become positive. All right, y'all, if the lattice lost something and became positive, that electron was probably no good in their life, you know. Okay, that was a really lame joke, but we're coming up to it. So with an intrinsic semiconductor, holes and free electrons are quickly neutralized. All right, so let's think about it. If I have, all right, let's just put in our own hole and, all right, so say I have a free electron here. I take that free electron and I put it in my lattice. I'm now going to have a full tetravalent bond where all my atoms and all my spaces are taken up. So I have a nice neutrally charged lattice with no reason or no mechanism to allow for the flow of electrons. Remember, electrons need to flow by having another electron to move with. You need a free flow electrons or non-bonded electrons to allow for the flow of electricity. So if I have here silicon where everybody is involved in bonding, there are no free electrons around. But what happens with silicon and germanium, just silicon and germanium, all right, as they heat up, some of these electrons gain energy and they leave the system. So they become a free electron. And what happens, if we zoom in a wee bit, right, what happens, we are going to end up with a space or a hole in our lattice. This hole is a hole, meaning it can now accept a new electron. The hole here has turned it into a positive particle or positive component, a positive atom or compound. So it is now positive. And what is a positive atom or compound going to do? It wants that electron. it is going to attract any free electron. So suppose this electron had left and gone its way, there will be another electron that's around. If there's any other electrons that are around, it will be attracted towards this hole because a negative charge will be attracted to a positive charge. So as soon as that negative charge is pulled into the lattice, that positive charge has been neutralized because positive plus a negative is 0. So we have a neutral charge now. And instantly, that very short, very short and brief moment that it had free electrons now becomes a neutral atom again. So intrinsic semiconductors do not have free electrons for very long. Why? Because as soon as a hole is created, an electron that has been liberated somewhere comes and takes its place. So if we were to apply an electric current into silicon material, what is electricity? Just free flowing electrons. All of those holes would immediately get filled up, and we have lost our positive charge, and it's going to become neutralized. And once it's neutralized, it's now an insulator again, wanting nothing to do with free flowing electrons. So it's now an insulator. So this sounds kind of useless. How can we have a material as soon as we put electricity in it, it now becomes an insulator? That's not going to help us conduct electricity. But they thought this is what led them to realize, like, no, for a very brief second, right? As long as a hole was created and a free electron was liberated, it did create some degree of electric current. But the problem was that these holes were rapidly filled. So let us find a way to, one, create excess holes, and two, create excess electrons. By creating excess holes, we are going to encourage the movement of electrons into the material. And by creating excess electrons, we are going to create the pathway for an electric current to flow into. So let's see what our extrinsic semiconductors look like now. All right, so we went from intrinsic, which is our basic semiconductor material, but is kind of useless in the world of conductors or of electronics because it immediately, as soon as you put on your power, all the holes get filled and we're no longer a conductor. So extrinsic semiconductors, which are semiconductors with impurities in it. So small amounts being 1 per million, as in every million silicon atoms, we can put one excess atom of a certain element. So let's read small amounts being 1 per million. Well, that's really 1 per million. That's like adding the whole of Trinidad's population. You add 1 and 1/3 of a person. That's not supposed to make any difference, but it does. All right, so small amounts being 1 per million of certain elements. Now, please note our language here. We talk about certain elements can be added to germanium and silicon without producing any distortion in the basic crystal structure. Now, when we have all our atoms like this, right, and we go, right, and we pile them up, they are going to have a regular structure. But suppose now I go and inside here I put a big atom or a small atom. Let's say I put a big atom in it. What's going to happen? It's going to distort. Okay, that's not working. But it's going to cause all the atoms around it to move and distort the material. We don't want the material to get distorted. You want all the crystal structures to remain in relatively same shape. So that's why only certain materials can be added. Materials being elements can be added to our pure intrinsic semiconductor, so it does not interrupt with the shape of the material. So the process um, of adding an external or an impurity to a semiconductor is called, now y'all, these words existed before popular words, So the process of adding an impurity to a semiconductor is called doping. No, we're not drugging it. All right, so let's avoid that joke right now. All right, so the process of adding any sort of impurities to our semiconductor is called doping. Now, there are very, very special types of material that we can use to add to our semiconductor material. So let's see. These are atoms which are added are often referred to as impurities. The atoms which are added are either pentavalent, being antimony, arsenic, or phosphorus. Pentavalent means what, folks? Anybody? Chemistry people? No, it's not adding penta, painter. We adding no paint to this thing.
It's five something.
Five. Penta means five, so five valence. So you are adding something with five valence electrons. Or trivalent, being iridium and gallium. Trivalent being three valence electrons. The type of impurity will determine the type of semiconductor. By adding a certain type of impurity to our semiconductor, we can get two types of semiconductors now. All right, so we're going to look at what happens when we add the pentavalent impurity and then when we add the trivalent impurity. So pentavalent, or the diagrams are there, good. When a pentavalent impurity is added, an extra electron is introduced to the system. Why is an extra electron introduced to the system? Let's look at this. If I have silicon that has 4, remember our outermost shell takes 8. Why so loud? All right, so suppose I go and add phosphorus. All right, suppose I go and add phosphorus. So phosphorus is coming to the party with 5 electrons. And those 5 electrons, only 4 of them can be bonded. Woo! Loud. Wow. Who's doing that? Rachel, please take off your mic.
Like she headphone causing static. I feel she trying to say something.
Well, you can say it in the chat. Rachel, do you have something to say, young lady? Okay, if I hear this again, I'm going to mute it. Thank you. Right. So what's going to happen when I put, oh, Lordy. Okay, I get back my pen. All right. When I put this pentavalent phosphorus and I bond it with all the other silicon, 4 of those pentavalent um, electrons are going to be bonded with the silicon and everybody is going to be nice and happy. But then we are left with this one excess electron. This one excess electron is going to become a free electron. And what is a free electron? A component of electricity. We need free electrons to allow for the free flow of electricity. So the main fact that it produces just by adding 1 per every million, our phosphorus atom is going to add 1 excess free electron to the system, and it's going to give the semiconductor the possibility of conducting electricity. Look at that, just adding 1 atom per million. We have now introduced a free electron because 4 of those electrons are going to be involved in valence bonding, while 1 is just left there free. It's going to be liberated because these materials, any free electrons are liberated due to heat. So let's continue reading. As a result, free electrons are readily available in the lattice. Lattice being your entire structure. Remember, this entire thing is crystalline, so we can call it a crystalline lattice. The pentavalent elements are known as donor impurities. Donor, why? Because we add an extra electron. So it donates an electron to the system. So it's called a donor impurity, and an N-type semiconductor is made. N meaning really simple, negative. N-type refers to negative charge carrier, meaning it has introduced excess electrons. So electrons are going to be the method or the mechanism by which electricity is transferred or conducted through our material. So what we're going to have here, um, our majority, whoa, what has happened there? All right, our majority charge carrier are going to be electrons, and the minority charge carrier will be holes. Now, what's going to happen? Just by the mere nature of our semiconductor materials, as it warms up, there are going to be a few of these silicon atoms that will liberate its own electron. This is the nature of the semiconductor material. It has a negative temperature coefficient, so that means as the temperature rises, electrons are naturally going to be liberated from the system. But as we saw just now, just look at it. Say that one electron had been liberated and is now running around or flowing around in the circuit. So this one electron is now free. What do you think is going to happen with this free electron from the pentavalent atom? It is going to come now, seeing a hole available. No, not you. Not you either. It's going to, okay, see all there. All right, let's see if we can get this one. All right, so it's now going to come and take the place there. So you see how the pentavalent atom contributes electrons in your system. But guess what? Because the silicon had lost one of its electrons and now this has become a free electron, the extra electron from the pentavalent atom goes and fills that space. But guess what? We still have a free electron in our system, right? That free electron did not get taken up and get neutralized. It continues what we call a chain reaction. So as one electron is taken up, another one is released. And it's going to happen so forth. So let's look at it here. The majority of the majority of the charges here are in the form of free electrons. And what had happened when that free electron, when that electron from the silicon had moved? What would we call this when one of our electrons had moved?
That's bonding the sharing one. We just call it.
We just learned a new name for it.
Or I don't know.
Anytime an electron moves, right, a hole is formed in our lattice. I could circle this whole day, right? As soon as an electron moves or leaves its place where it's supposed to be, a hole is formed. And that hole is an inherent positive charge in your material. So you can see here, our minor charge carrier will be some of the silicon atoms will lose an electron. And when an electron is lost from our silicon atom, a hole is formed. But if we look here, we have, if you want to see, we have two free electrons and one hole. So which one there do we have more of? We have more of the electrons, so that's why your electrons are your majority charge carriers, and the minority charge carrier will be your hole. Hole being a positive charge that has formed due to the loss of an electron. Holes don't last for long. Well, not for yet. We're going to see about holes just now. So this is what happened with a pentavalent impurity. One, let's go through it. A pentavalent impurity has 5 excess electrons. So with 5 excess electrons, that means 4 of them are going to be involved in bonding. 4 of them are involved in bonding, while we have an excess electron here that can allow for an electric current to flow. All right, this excess electron here is what allows for excess electrons or for more electrons to flow through the system. So this is why pentavalent impurities are called donor impurities, because they add an electron, right? And they are chat message. Okay. All right. And when you have a donor impurity, obviously, if we add excess electrons, we're going to become negatively charged. So we get an N-type semiconductor being formed. You all have to learn what type of atoms are added to create an N-type semiconductor and what are your charge carriers in an N-type semiconductor. But some common sense will tell you N-type means negative. So that means my majority charge carriers will be electrons. So if the majority of my charge carriers are electrons, then my minority charge carriers will be holes. And we can see here, just here with one bonding, how we get one hole with two free electrons involved. So obviously one is more than the next. So let's move on. Oh, that got really thick. So if we zoom in here, we can look at two other examples. Right, we have a silicon and SB is antimony. All right, if you're not too sure, go and look up what antimony is, why it has an SB instead of the antimony. So the antimony has an extra electron. So 4 of the electrons involved with antimony's bonding will get bonded to a silicon very comfortably. And then we're going to be left with a single donor impurity meaning it's adding electrons to the system. Similarly, here we have germanium and arsenic. All right, your arsenic is not always dangerous, neither is mercury. We need mercury in our vaccines to have some sort of delivery system. Remember, when things are bonded with other things, they're not so dangerous. All right, best example, salt. Salt has two of the most corrosive materials whatsoever, but we bond them together and they're left with something as boring as salt. All right, so when we introduce the arsenic into the germanium, the arsenic here, if you see, 4 of its atoms, of 4 of its electrons are bonded to the germanium system. So here we're going to see that they are bonded to the germanium. And then we are left with one free electron. And this one free electron is going to contribute to increasing the conductivity of our material, because we just need one free electron to encourage the free flow of electricity. Remember, there are millions and millions of atoms. So when you have millions and billions of atoms, that one is going to add up. So let's read and continue to the next side. The addition of trivalent impurity increases the number of holes in the material. All right, why will it increase the number of holes in your material? Let's look at it. If I introduce a trivalent material was gallium. All right, so say I have gallium. Gallium has only brought 3 electrons to the party. All right, so it's only going to be able to bond to 3 silicon. And this one silicon here wants a bond to go with, right? It needs a bond. So we are left with a space, right? And this space is called a hole. Remember, the hole here is your positive charge. If I have a space here where an electron must go in and there's no electron there, that means it's going to readily take an electron, right? We can get any electron that exists in the system. If it sees a hole, it's going to take that electron and accept that electron. Holes are positive charges, so that means it wants a negative charge. It's going to attract a negative charge. So it's going to pull a negative charge from somewhere, and guess what? By pulling a negative charge, we have thus created a flow of electrons, which is electricity. So you saw the other one, it created excess electrons, right? And those excess electrons are going to create electricity. But for your trivalent impurity, it's going to pull an electron. And the mere fact that we are pulling an electron is going to result in the flow of electrons, giving us electricity. So you see, it's two different mechanisms that at the end of the day give us the same thing, which is electricity flow, electron flow. So let's continue reading. These These impurities are known as acceptors. Why it is acceptors? Because they will gladly take and accept an electron. Being positively charged, that means we're going to gladly accept a new electron into the system. So it's called an acceptor. Since they accept electrons, right? Yeah, we came up with really complicated terms for this topic, acceptors and donors. A trivalent doped semiconductor is called p-type. P-type, so because it's positive, right? And p-type refers to positive charge carrier. So what happens here? The majority charge carrier will be a hole. Now, how is it going to create a hole since it already has a hole in it? Now, just say, suppose we have a silicon somewhere around. Oh, come on, behave. All right, suppose I have a silicon here, and that silicon has a thermally generated electron. This electron here wants to move because it has enough energy. It's gained enough energy from the environment and it's ready to move. So that means, it just there, it was just climbing with the other silicon electrons, but it has no reason to stay. It sees a hole. It gets attracted to a positive charge. So that positive charge is going to pull this seriously? That's what you're going to do now? All right. It's going to pull this electron, right? It's going to take this electron and fill that hole. But guess what happens? When it pulls that electron from the original silicon, what happens? What now forms at that silicon atom? Oh, you can't see that. What happens here? A hole is now created. Yes, Jabari?
I was gonna say whole now, but yes, it already so.
Oh, I should speak a little slower. I'll try to talk a wee bit slow. See,
But I understand.
my brain can't even say to talk slower. I stuttered and stopped. So let's look
Yeah.
at what our charge carriers here. We have our gallium bonded with our silicon. The mere fact that the gallium is bonded to silicon, we have a hole in the system because there is a space for a negative charge to come into. This positive charge or this hole is going to attract any liberated electron or any electron that is ready to leave or has been excited and can leave its system. It's going to take that electron. Let's put this another color, right? It's going to take that electron, this, right? Right? This is our free electron that first comes from our nice 4 electrons in the silicon. It's nice and simple. Those 4 electrons are bonded to 4 other electrons. Everything is nice and stable. Our properly filled shells, 8 electron shells. But because that electron is thermally excited, it is ready to move. And it is going to want to be attracted to a positive charge more than stay here with a whole bunch of negative electrons. So what happens? This negative charge will move. And the mere fact that we have, let's count it, we have one, 2 holes and 1 negative charge. So what you're going to see here, your majority charge carrier are holes because you have 1 hole pulling an electron and therefore creating another hole. And guess what? This hole is going to want to pull another free electron anywhere in the system. So if there's a free electron or an excited electron, right, that hole is going to attract it. And guess what happens? When that electron leaves the other one, another hole is created. So it's a chain reaction. As one is generated and pulls the next one, hole generates, right? That hole is going to pull an electron from somewhere, right? And where that electron came from, another hole, and so forth and so on. So it's a chain reaction. But if you look here in this whole system, we have one electron, two holes. So our majority charge carrier will be our holes, and our minority charge carrier will be our electron. Y'all, that made sense? I know it's a
It
new,
actually did. And it's chemistry.
and
How?
it's chemistry. You see, if I had like chemistry, I could teach chemistry, but chemistry wasn't too much of a friend now. All right, look, we can
I feel
have
it.
what?
I say I feel it with the chemistry not being a friend.
Uh, we said for
Chemistry,
bio.
man
Ew,
thing.
ew.
Ew,
I don't
I
like
hate
bio.
bio.
Look, who doing bio again?
Me, I hate that. Ew. Oh
I
my
don't.
god.
I don't like bio because it had no maths, honestly. Because I love biology, y'all. You all know I know everything about natural world, and I could explain anything about the natural world and biology and genetics, but it has no maths. So it bored me to tears in school.
Very
Right.
boring.
Right. Not to say I don't like. People think that I have something in bio because I talk so much about biology, but to study it, I'm bored to tears. Same thing for astronomy. I will never study astronomy, believe it or not. If I have to go back and study, it's going to be something in geology or geophysics or something, or probably meteorology, but not astronomy. Imagine me. I do not want to study astronomy. So,
That's what?
right? So, let's look at here an example. I have silicon bonded with a trivalent boron atom. So I have boron. Boron has 3 electrons. So that means that boron is going to bond to only 3 silicon atoms. So what happens with this fourth silicon atom? This fourth silicon atom has a hole, right? Meaning it has a space where, hello, I want an electron. I need an electron to fill my 8 electron shell. So this hole here is where okay, the screen moves on itself by itself sometimes. All right. So what happens? This hole is a result of our trivalent boron being introduced into our silicon lattice. And because of this hole being a space one electron should be or a positive charge, this hole is going to want to pull an electron towards it. And we know the movement of any free electrons. I'm saying this over and over and over, right? But the movement of an electron creates electricity. All right, you all think we did chemistry before? We're going to do chemistry now. All right, that's to tell you all, the further up you all go into chemistry, the more physics you're going to see. Same thing, the further up you go in biology, the more chemistry you see. And likewise, the further up in physics you all go, the more maths you can see. Don't ask when you go further up in maths what happens. Anybody want to ask what happens when you go further up in maths?
You'll get mad.
You explode. Yeah.
There's a word. You
Become a mad scientist.
descend into madness.
Of course.
Yeah.
Yes, you do now.
No, I'm a physicist, boy.
I say,
Right? Let me just pause this so the rest of the class will hear this conversation. Conduction band theory. All right, that should take us a few minutes to finish. Yeah, man, we could do a little bit in the 7 minutes left in class. All right. So, reading in the isolated atomic structure, meaning we're looking at pure atoms right now. We're not looking at holes, free electrons, semiconductors. We're looking at materials, how they exist naturally. Any atom, every atom that we know about so far. In the isolated atomic structure, there are discrete energy levels associated with each orbiting electron. Each material will in fact have its own set of permissible energy levels for the electrons in its atomic structure. The more distant the electron is from the nucleus, the higher the energy state and any electron in the atomic structure. So you all ever notice it's easier to break down large atoms than small atoms. Really, really small atoms form ridiculously strong bonds with no matter what's it bonded with, either covalent bond or ionic bonds. Those are the two strongest type of bonds that exist. But once you start getting bigger materials, as soon as your atom starts getting larger and larger, it has a lot of energy contained in it. And an electron, not electron, an atom with very high energy electrons are more likely to lose one or two of those electrons. Hence why most of our materials in most of our materials or atoms with um, large structures or a large amount of shells are all metallic. You'll have noticed all of those materials down the line are metallic. Why are they metallic, or how do we know they're metallic? What results in them being metallic? Because being that large, all of the electrons, especially in the outermost shell, are very, very high energy. So that means it makes it very easy for them to move away from the material or move away from the atom and become a free electron. Right? That's why we have very few pure ionic atoms and very few pure covalent atoms in a lot of metallics. Why do we have so many metallics? Because they lose their electrons, all right? And those electrons are easily lost because they are high energy electrons. See how we can explain chemistry using physics? All right, and we're going to go into this even more in depth in module 3. So reading again from the handout. Between the discrete energy levels are gaps in which no electrons in the isolated atomic structure can appear, not appears. I don't know where this comes from. As the atoms, okay, I need to sort out this. As the atoms of a material are brought closer together to form the structure, there is an interaction between the atoms that will result in a particular orbit of one atom having slightly different energy levels from the electron. So what happens when we take one material with our electrons, say these are our electrons in different gaps, right? Our electrons in different gaps. When you bring another atom, we can get some of those gaps either interlocking with each other or overlapping with each other or joining each other. So this is what happens. You are going to end up getting different things happening. You're going to have materials that stay far apart from each other, meaning the electrons do not interact with each other whatsoever. Sometimes those electrons are brought closer together because we have reduced the amount of energy in the system, or sometimes those electrons bond together, right? You know, we already see how the kind of materials we're going to get. One electron's side from an atom can join up with the next one and give us a different type of um, bonding. So we can have two that want nothing to do with each other. We can have those that are brought very, very close to each other to kind of encourage motion. And then we have the next one that brings everybody joined together in one shell or lattice. That's all. Reading down. So let's read and see what we have here. We are going to look at energy levels or energy bands. These energy and level bands are the same energy levels, bands, and shells you have in chemistry. What's our first shell called, you all? What shell? What's the name again? Chemistry people, what's your first shell named? Use your nucleus. You have your first shell, second shell, third shell that broken up into three subshells. What is your first shell in your atom called again?
The inside shell.
The outer shells?
They have names for these shells. Chemistry people, come on. You all remember things called the P, the N, the S, and those type of shells?
Very Asmus.
The S is the first shell?
I think so.
Don't let me find a chemistry textbook, you know. Right? Really? I could have swear the first shell was a P shell.
Nah, it's S and P and D.
Oh. Right? So this is where they got the names of our shells. Right? This is how they came up with the shell values in our atoms, and not by random. It's like, well, you know, let's put the first shell to have 2. Let's put the second shell to have 8. Let's put the third shell to have 18, but those 18s are broken up into 2, 6, and 8. No, 2, 8, and 8 or something. Right? So there's a reason why we have these shells, because there's a certain amount of energy that electrons can have. The first shell that we have can only take 2 electrons at a certain amount. Oh yeah, look at it. It is P. It is S. So first shell is the S shell. Second shell is your P. All right. That D shell makes no, I don't remember that, but all right. And so forth. So what we have here, for any atom, if we have our nucleus existing here, the further away you go from the nucleus, the more energetic your electron is going to become. Why is it going to be more energetic? Because it doesn't have that strong bond pulling it to the nucleus. Remember, the nucleus is nothing but positive charges, and positive charges are going to take that negative charge and interact it in a very, very, very strong bond. One of the strongest bonds, if not one of the strongest bonds in the universe, is this bond between your electron and your proton. But the further away you go from your nucleus, right, your electrons need a lot of energy to continuously keep on going around the shell. And because it has so much energy going around the shell, one is going to go and say, all right, bye-bye, and go its own way and become a free electron. So the further away you move from your nucleus, the more energetic your atom becomes. So what we're going to have, we have, let's look at it here. Let's go a wee bit closer. All right, we'll continue this next day. So we have what we call valence bands. Valence bands are bands where your electrons are bonded. Then we're going to have the gaps between our bands, or the gaps between the bands are areas where no energy exists in your natural material, as in the atoms will not exist in there. That's why we don't have subshells. Well, not yet. When you have your nucleus, you have your first shell, then you have your second shell. There is no in-between shell between these two. It does not exist. All right, just same thing for the third shell. There's no in-between the third and the second shell. Is either the first shell, the second, or the third. Now the third has 3 different type shells, but there's still no in-between between the third and the second. There's no 2.5 shell. There's no 2.8 shell. They exist at this is where we can introduce physics, quantas or packets of energy at certain values. So what we're going to have, we're going to have our band gaps. The band gaps here are where no set of energy can exist. It either goes from 1 to 2. Just like how electrons have a set value of 1.6 by 10 to the minus 19 coulombs, there is no electron with a charge of 0.5 by 10 to the minus 19 coulombs. None. There's no charge that has 1.9 by 10 to the minus 19 coulombs. It's either 1.6, then 3.2, then 4.8, right? They'll exist in packets of numbers. So we have here energy gaps. And then after the valence band, we have something called the conduction band. What happens here? The conduction band, we are going to have free electrons forming, and free electrons are what allow for the conduction of electricity. So we are going to first have our bonded bands, our bonded electrons, right? And as we go, that electron goes further away from the nucleus, they're going to become more excited, and the chances of them becoming liberated and free electrons increases. So they go from becoming a valence electron, as we just saw in our trivalent and pentavalent impurities. It's very easy. As soon as that free electron forms, we are going to now become a conductor of electricity. So this is where we take a bonded electron And as soon as that bonded electron becomes a free electron, we are now going to go into the conduction energy levels. So that's it for this one. All right. Let's just read up this last one and then we'll wrap up for the day. There are boundary levels and maximum energy states in which any electron in an atomic lattice can find itself. And there remains a forbidden region between the valence band and the ionization level. Anybody want to tell me where you think the ionization level is going to exist in this diagram? What does ionization become? Tell us. What does it mean to ionize something? Chemistry people. Don't let me call names, huh? And this is Form 5 chemistry. What does it mean to ionize something? You all are going to look that up, go and review what is ionization. Why I'm telling you that not only do we do it in this topic, we're going to be doing it in Module 3. 2 topics in Module 3, we must look at ionization. So you all go and revise your basic chemistries. Let me tell you from now, all right? Anybody, is my mic working? Is that I'm hearing everyone? Let me check. Don't know if everybody talking and I'm not hearing them. No, I see nobody talking. Can anybody tell me what is ionization? A blank. Okay. You all read that up and we'll do this the next day. All right. So let's finish this all up. All right. So next day we will look at how we have different energy levels for our insulators, semiconductors, and conductors. Then we're going to look at band theory, at how a semiconductor works itself, how it works down to the energy levels, where we're going to look at the physics part of it. And then we're going to look at the junction diode, because a plain semiconductor, a doped semiconductor by itself is again useless. But when we take two semiconductors and bring them together, we form a diode, and that diode does magical things that allows for our world as it is to exist. So you're going to wrap up there, you all. Let's close this off.